These are your 9-3 transformations of quadratic function notes. In this section, we're going to learn how to transform quadratic functions. We're going to talk about parent functions and then looking at a different form of the equation of a quadratic function and how each part of that form relates to the different transformations of the quadratic function. So in the beginning here, we're just going to review what a transformation is, some terminology for you. A transformation is a motion that changes the position or size of a figure or graph. You might have talked about these in middle school. You will talk about them again in geometry. And then throughout the course, we talk about transformations of graphs throughout Algebra 1 and Algebra 2. There's different kinds of transformations. The three ones that we're going to concentrate on in here are translations, dilations, and reflections. Another common one is rotations, but we're not going to talk about that in this section. So of the transformations, a translation slides the graph horizontally or vertically. The graph does not change its orientation, meaning the direction of opening stays the same, left is still left, right is still right, up and downs are still the same. So the best way to describe it is you're taking that graph and you're sliding it across the page, either left to right or up and down, or a combination of directions. A dilation makes the graph wider or narrower than the parent function. So it will, another way we describe dilations when we're talking about a graph is we talk about stretching the graph vertically or compressing it vertically. And so when you stretch it, it becomes narrower, and when you compress it, it becomes wider. It squishes down and widens. And then a reflection, you guys have heard that term before. It's a flip. It reflects a graph over a line, and so it will flip the direction of opening. So when we're describing these transformations, there's another form that better represents the transformed form of the quadratic. So this is called vertex form. Just like lines have slope-intercept form and point-slope form and standard form, quadratics have another form, and this is called vertex form. And so we already studied standard form, and that's your ax squared plus bx plus c. This is just another way to write the equation of a quadratic, and this time the letters represent the transformations. So instead of a's, b's, and c's, we now have a's, h's, and k's. And so it's going to, each of those letters describes a different transformation from the parent. What I would suggest at this point is to get either some highlighters so they don't bleed through your notes, or maybe some colored pencils or pens to go over and label in color, because it's going to be important that you understand what sign is making the graph go in which direction. So if you look at these first two boxes here, I've got H and K. And if you look at H and K, they're really the same exact parabola. If you were to shuffle them all together on top of each other, they would fit. I know K doesn't look that way, but it's true. They're just showing you a little bit of the red. They're showing you more of the green. That's why the green looks bigger, but they were actually all the same width of the opening. In all of these examples, the blue graph is the parent function. So the blue graph is the function when h is equal to 0. There is no motion. The red graph is when h is greater than 0. And when h is greater than 0, when that value is greater than 0, it's going to shift the graph to the right. What I want to mention here, though, in vertex form, the vertex form looks like a minus h. So it's that whole idea of it looks like it's negative. But if you plug in a positive h value, it's still going to look negative. So I want to mention that for the red graph, that would be something like y equals x minus, in this case, 2 squared, because it shifted to the right 2 units. So even though in the equation it looks like a negative, it only looks like a negative because that's what the vertex form does. It's saying minus there. So that minus is part of the form, and the 2 is positive. The h value is actually positive. Now the green graph is when h is less than 0, or when h is negative. And if you plug in a negative h into vertex form, you'll have a double negative. And so in this case, it looks like it shifted 2 units to the left. And so this would be the equation x plus 2 squared. Even though it looks like a positive 2, if they plug a negative h value into the form, it would become minus a negative 2. Well, minus a negative becomes plus positive, so plus 2. So I'd like you to write those down so you understand. Even though it looks like a positive, the green is actually a negative h value. Even though in the equation the red looks negative, the h is a positive 2. The negative comes from the form. So the h value is your horizontal translation. H is a horizontal translation. It moves the graph horizontally. And I like that because H for horizontal. H is also with the X, so it's easy to keep track of that your H value is the motion of X. Your X motion is your horizontal axis. So then if you look at K, your K value is a vertical translation. This is your vertical translation. So I'd like you to write the actual transformation that's going on here. It's a translation. K is a vertical translation. I like the K for vertical, the K and C sound. Now this is different than H. It's actually true to the sign. So if you're going to go up, if you look at the formula, up, this is positive K. The sign of K is going to show. It's not going to be the opposite. So again, the blue graph is our parent function. That's just when K is equal to 0. There is no number added or subtracted from the parent. Your red graph is when K is a positive. And so that equation would look, in this particular case, it went up 2 units. And so it would be x squared plus 2. Or another way of writing that is x minus 0 squared plus 2. By putting the 0 there, you can see that there is no h. Sometimes people get confused when there's no h. And then the green graph shifted down 2 units. And so the green graph is when k is less than 0 or negative. So y is equal to x squared minus 2. And so that is our shift up or down. Remember, we're always talking about the parent function. What are we doing to this thing? If you look at the parent function, there is the h is 0, the k is 0, your a value is 1. Everything is very standard. So h is a horizontal translation, k is a vertical translation, and then we've got that lovely a value. The a value actually does 2 different things. So let's look at the left-hand side first. Your a value, and you already knew this from before, it's the same thing as when it's in standard form. The a value decides the direction of opening. And so if a is greater than 0, if a is positive, then the graph opens up. If a is less than 0, or another way of saying that, if a is negative, the graph is going to open down. And so if you look from the blue to the red graph, the transformation that's occurring here is this is a reflection. It's reflected over the x-axis. And the other thing that A does is A determines the opening, the size of the opening. And so again, we've got blue, green, and red. The blue graph is our parent function. The red graph is showing when the A value is greater than 1. Now they put absolute value signs around it because they really don't care about the sign. 2 and negative 2 are going to be the same width, just one of them will be upside down. 3 and negative 3 will be the same width, but that one will be upside down. So we really don't care about the sign of this value. We're just looking at the numeric part. So if it's greater than 1, 2s, 3s, 3.5s, -4, they're all greater than 1, it's going to stretch vertically. Stretch vertically means it's going to get narrower because we're pulling the graph upward faster. It's stretching it vertically because we're multiplying it twice as big or 3 times as big. Then if the number is a fraction, a proper fraction, somewhere between 0 and 1, again, we don't care about the sign, so 1/2, 5/3, no, not 5/3, 5/7, a proper fraction. The graph will be compressed vertically. So think of something sitting on the graph and it squishes it down, making it wider. Now what's going to happen here is you're going to think bigger number, bigger graph. No, not necessarily. It's going to be bigger number, the bigger the y value. The quicker you get to the y value, so it's going to be a narrower graph. And then the smaller the y, the more squished it's going to go. It's going to go out more than it's going to go up. And so A is sort of like our slope of A. A is sort of the slope of a quadratic, in a sense. Slope is really rise over run. These things don't rise and run, but in a sense, you could think of it that way. So if you have a slope of 4, you're going to be steeper, stretched vertically. If you have a slope of 1/4, you're going to run 4 for every 1 that you rise. You're going to be compressed vertically. And so this would be our dilations. A is our dilations. Okay? So let's just go ahead. We don't have to graph them, but let's just describe what that's doing to our graph. So for number 1, what it looks like is all we have is a +10. So the only thing that changed is there's a k value. I'm going to write down the vertex form here just so you understand what it looks like. And this is how the book writes things. Number 1 is how the book writes things. I know I don't see an A, I don't see an H, and I just see a +10. So a helpful hint, until you get used to this, is put in the A value. If it's missing, it's a 1 out in front here. If there is no H value, expand that x squared. Okay, that's still x squared, it's just expanded now so you can see where H would be. And then the +10 goes out here. So if it helps, you can put it into that vertex form. And now you can clearly see that the only thing that's happening here is the +10. That is your k value. So describe how the graph of each function is related to the graph of the parent. This graph is a vertical translation, 10 units up. Okay, so be specific. It's a horizontal or vertical. And then vertical, you got to say if it's going up or if it's going down and how much. In number 2, we still have that squared term. I'm going to rewrite it though. We have an H value, a +2. I'm going to expand that x squared so I can see the H value and then the k value. So in terms of the parent function, this graph took the parent function. There's a vertical translation of 1 unit up. And then the 2 is going to have a dilation. So it's dilated by 2, and that's going to stretch the graph vertically. So it stayed in the same spot horizontally. It's still facing upward. It's just narrower. And it's narrower because we stretched it vertically. I'd like you to use the term stretched and compressed vertically. It carries out through the rest of your math career. So let's get used to that language. In number 3, there is no A value, but there's an H and a K. So I'm just going to add the A value here as 1. Okay? And so the only thing that's happening with this parent function is that it was translated. It's translated twice. So this graph is translated. It's translating the parent 3 units to the right because my h value here is a positive 3. It looks like a negative 3, but it's actually a positive 3. And it's translated 2 units up because of the positive 2, the positive k value. And number 4, our last one, it has all the pieces. It has an a value. My h value is a negative 5 there, and then it has a k. So we got to talk about everything that's going on here. It's translated, the h value of negative 5 is going to translate it 5 units left. The negative 7 for the k value is going to translate it 7 units down. The 3/4 is a dilation. And what it's going to do to the parent function is going to compress the graph vertically. And when it compresses the graph vertically, it's going to be wider. The only thing that I haven't shown you here is if there was a negative a value, which would reflect it, and it would be facing down. Okay? Number 5, it says, which is the graph of y equals negative 3x squared plus 1. So I'm just going to expand that really quick. Negative 3x minus 0 squared plus 1. And so this looks like the negative tells me, this negative 3 tells me we're going to have a reflection. So right now I know that f is out and I know that j is out. And then looking at the other two, I know that I did not shift to the left or to the right any. And I went up 1. And so looking at these graphs, g goes up 2 and h went up 1. Therefore, h is the correct answer. So just applying those transformations that we learned in class doing our activity. So here are your 2 questions. I want you to write in your own words what a, h, and k does to the parent function. And then I want you to come up with your own equation. There's more than one answer. And you're going to give me an equation of a function that would stretch vertically, that's reflected over the x-axis, and that's translated 2 units up and 2 units to the left. Good luck.